So this is lecture 30, so we're going to do the moment generating function. So is there anybody here who is planning on taking complex analysis next semester? Okay, so the people in complex analysis will say Fourier transform. Here we will say characteristic function. They're very similar. We talked about I being the square root of -1. It turns out that instead of looking at the moment generating function, you could look at something very similar called the characteristic function. The only difference is you put in an I. But it makes an incredible difference in terms of convergence and existence properties. So what I want to do is I want to do some examples first, show you a little bit about why we care so much about generating functions and whatnot, and then show why moment generating functions are a little bit easier to work with for a lot of problems. So the way, remember, the generating functions are defined is the an is the probability our variable equals n. This is fine if we have something that's discrete, but if we have something that's continuous, this is going to be a little bit harder. And this gives you some idea of why the generating function can't be the end-all, be-all for this class, because we have continuous random variables. And we want to have a sum of an s to the n. If it's continuous, we can't put something nice there. All right, so what I want to do is go back to something we've done before. The sum k goes from 0 to n of n choose k squared, which is the same as the sum k goes from 0 to n of n choose k, n choose n minus k. We showed this was 2n choose n. So we gave a proof by story of this a long time ago. And I want to show you how you can prove this using generating functions. Stories are often hard to come up with. If we can have a more mechanical procedure, that's useful. So let's let g of s be the sum, k goes from 0 to n, we'll call it g sub a, of n choose k, s to the k. Anybody know what this generating function equals? Or what we could do to make the function look a little bit simpler for evaluating? And I only know how to do 3 things. I can add 0, what else can I do? I can multiply by 1, and what else can I do? I can take logs. So one of those things is going to help. Any thoughts on what we should do? Okay, and how should I write 1?
Parentheses 1 minus s to the n minus k over, like, parentheses 1 minus s.
We could do that. I think there's a simpler way to multiply by 1 than that. What does this look like? What theorem should we be thinking about? The binomial theorem. So if I have n choose k, s to the k, I should have 1 to the n minus k. I haven't changed its value, but now I make this look a lot easier. This is why I really want to spend a lot of time in this semester going, this stuff is hard. But if you can master this, you will be able to look at the subject at a really high level. Doing nothing is difficult. You have to figure out how do you want to put this in. This is like auxiliary lines in geometry. If you find the right line to draw, the problem becomes trivial. But it's hard to figure out where that line is. Well, now by the binomial theorem, this is just going to be 1 plus s to the n. So if I look at GA of s times GA of s, this will be a sum, k goes from 0 to n of n choose k, s to the k, and it would be a sum of L goes from 0 to n of n choose L, s to the n minus L. I'll write it this way. Yeah. L. And this is going to be 1 plus s to the 2n. Right? And now we have a convolution, basically, of 2 series. And so when I look at the middle term, what would be the term that would be s to the n? How do I get an s to the n? If I choose k here, I have to choose n minus k here. So if we go, on this part, the coefficient of s to the n is going to be the sum k goes from 0 to n of n choose k and then n choose n minus k. We have to take L being n minus k. So that's what the s to the n coefficient is going to be. Now, if I look at 1 plus s to the 2n, the coefficient of s to the n is going to just be 2n choose n. And so they must be the same. So this is another way to prove results like this through generating functions. Okay? And it also tells you a little bit why we want to write it as n choose k, n choose n minus k. When we have the convolution, when we're summing the two things together, they build in like this. Okay? So there's a lot you can do with these generating functions. We are just scratching the surface right now. Okay. The next thing I want to do is I want to do an example. So I want to do a continuous random variable. So let's take x is exponential with parameter lambda. And so let's calculate its generating function. So what would we mean for the generating function here? So let's think back. When we had discrete, we had the generating function of x was the sum, n goes from 0 to infinity, of the probability x equals n times s to the n. And we saw that there was a nice way to interpret this. How could we interpret the right-hand side? Yes? The expected value of s to the x. And basically this was just saying, if we just mentally move the s to the n over, it's going to just be the expected value of s to the x. This definition is really nice if we have a discrete random variable that takes on values at non-negative integers. This definition, is really nice in general. I can define this for a whole slew of things. So let's take this as our definition of the generating function. And that will be something that we can work with. So now, we will define the generating function of a random variable to be that expected value. So definition, the generating function of x is going to be the expected value of s to the x. So if x is exponential with parameter lambda, this means the density function is going to be 1 over lambda e to the negative x over lambda if x is greater than or equal to 0, and 0 otherwise. So now all we have to do is just do the algebra. And so this is all in the book, expected value of s to the x. All right, so this is now going to be the integral from 0 to infinity, because my random variable has no probability before 0, so I might as well just start the integration at 0. And then I'll have s to the x, 1 over lambda, e to the negative x over lambda dx. Okay, how do we do this integration? Yes?
By parts? No, that doesn't make sense. Sorry. No,
Okay. Again, so much of this is trying to find the right way to express something to simplify the algebra. Okay. There should be one piece here that you do not like for the integration. Which piece do you not like? Yes? Yeah, we don't like s to the x. We are allowed to discriminate on the basis of base. Right? What is the best base for mathematicians? E. E, not 1. For computer scientists, I'll accept 2 or 3. For somebody in Div 1, I might accept 1 because they might not understand exactly what we mean by a base. But for us, we want base E. Why do we want base E? And it's not because our founder was named Ephraim, yes.
It integrates really nicely.
It integrates nicely, it differentiates nicely. What's the integral of e to the x? E to the x. What's the derivative? E to the x. When you have s to the x, you have to worry about all these logs and whatnot. So what we're going to recall is that I can write s to the x as e to the x log s. And I'm now writing it as an exponential. And if I do that, I have the integral from 0 to infinity, 1 over lambda, e. Now I'm going to have a negative x over lambda and an e to the x log s. So I'm going to write it as negative 1 over lambda minus log of s times x dx. And negative times negative is a positive, so this is correct. What does this look like? Or at least what is this close to? So you really want to look at an integral and get a sense of what is it saying. Do you think this integral always converges? So no matter what value of s I put in, this is going to make sense? Yes?
S has to be positive.
S has to be positive, so if s is a negative number, good. What else?
I guess if the log s is really large, then that's going to be really small, and then the negative, it'll make the e to the power really big.
Right. So if the log of s is greater than 1 over lambda, this is a negative number which becomes a positive number, it blows up. So you need the log of s to be less than 1 over lambda. So this is going to give you some idea of where this integral can exist, which makes sense. You know, if my function is increasing too rapidly, the exponential decay is not enough to make things finite. Okay, so let's assume that the log of s is less than 1 over lambda, because otherwise it's a done lecture. What does this integral look like? This looks like something you've seen before. So we could, of course, integrate this directly. But if you think about it, this looks a lot like something you've seen. It looks like an exponential random variable. It looks like an exponential random variable with parameter 1 over 1 minus lambda minus the log of s. Because remember, the way we define things is it's supposed to be downstairs. So to move this downstairs, I think we would want it like this. Well, if I just change the normalization constant here by multiplying by 1, then the integration just comes and just pops right out. Right? It's almost an exponential random variable. So if I just change things a little bit, and again, the whole point of this is we could do this integration directly. I could do the change of variable. It's not that bad. But I want to really highlight that a lot of times, if you can show that what you have is very similar to a probability distribution, and you know probability distribution integrates to 1, you can just figure out what do you need by the normalization constant. So we can rewrite this as it equals, I'll pull out the 1 over lambda. I have an integral from 0 to infinity. I have an e to the negative x divided by 1 over lambda minus log of s inverse dx. So then I have to have a 1 over lambda minus log s inverse. And then I have to multiply by 1 over lambda minus log s inverse. What is this integral equal to? So you go to 1. So then I have a 1 over this. The lambda comes in, and I get 1 over 1 minus lambda log s. And hopefully I haven't made any algebra mistakes. So if I've made an algebra mistake, I apologize, but I think something like this is what we get at the end of the day. That we can evaluate this, and we know that this must be, we need log of s is less than 1 over lambda. And if you look at what's going on over here, oh good, this kind of makes sense. If log of s is now greater than 1 over lambda, this becomes negative. And my expected value of a positive quantity should not be negative. So it's good, it makes sense. There's actually a good chance I did the algebra correctly. So again, the idea is to be able to see how to do these manipulations. You could do the U substitution, but you can actually bypass this because we've done this already. So this is the this is the generating function of an exponential. Now, sadly, we do not have the same formula for continuous random variables. If two continuous random variables have the same generating function, they may not be the same. Okay? And then what you could ask is, well, what if I have the sum of two exponentials? Is the sum of two exponentials an exponential? And you could see what it would look like over here, and you'll actually get that, no, exponential plus exponential is not exponential. Okay, any questions on how we do this calculation? So here, the generating function is not going to exist for all values of s, but it will exist for s in a certain region. Okay. What's the nicest property we've seen about generating functions so far? And I've said that this is one of the things that we're going to use when we get to the proof of the central limit theorem. What's so nice about generating functions? What was that great theorem? Yes?
Was it the sums of two generating functions equals
Close.
the generating function of the sum?
Right. The generating function of a sum of independent random variables is the product of the generating functions. Right? So this was the theorem. XY independent implies the generating function of x plus y of s is the generating function of x times the generating function of y. Now, we only proved this last time for discrete random variables. Let's see if we can prove this in greater generality. So the generating function of s times the generating function of y is going to be the expected value of sx, expected value of sy. The generating function of x plus y of s is going to be the expected value of s, and then this variable x plus y over here. So what's s to the x plus y? That's s to the x, s to the y. I'm not going to go through all the details. The details are in the book. But what's the expected value of a product? Yes?
The product of the expected values?
Always?
Only if the variables are.
So as independent, the expected value of a product is the product of the expected values. And that finishes the proof. So this is one of the reasons we love generating functions. The generating function of a sum of independent random variables is really nice in terms of the constituent pieces. Okay, so now it's time to move to moment generating functions. And really, the only difference between moment generating functions and generating functions is a change of variable. And it just turns out this is a better quantity to look at. So I was actually talking with the our stats wing of the department yesterday as to do they actually look at characteristic functions in higher level stats classes. And I was told that you actually will see these as well. So I will state what a characteristic function is. So we have the generating function gx of s is the expected value of s to the x. Has anyone taken a stats class where you've seen characteristic functions yet? Okay. Something to look forward to. The moment generating function of x at t is the expected value of e to the tx. And the characteristic function of x at t is the expected value of e to the I tx, where I is the square root of -1. So this is the moment generating function, and this is the characteristic function. Is the moment generating function similar to the generating function? What do you think? Are they completely different quantities, or is there a nice connection between? Yes?
Isn't just e to the t equal to x s?
Yeah. If you just put parentheses like this in your mind and call that s. So I'm feeling generous today. I'm going to call it a theorem. I think this is being a little kind to it to call it a theorem. But the moment generating function at t is equal to the generating function at e to the t. And you can simply go in the other way. If you have the generating function at s, this is the moment generating function at what? Log of s. What this means is that we can basically inherit results from generating functions to moment generating functions. I'm not going to bother reproving things. It's a change of variable and then change back. If you're going to study an object, the nicest thing, the nicest property for it to have is for it to exist. If I give you a generating function or a moment generating function, it would be really bad if it didn't exist for any values of input. Can somebody give me a value where no matter what random variable I give you, the moment generating function has to exist at that value? Yes?
If s or like t equals 0?
Yeah, if t equals 0, you're getting the expected value of 1. So the moment generating function will always exist when you put in t equals 0. Will it exist for other values? So clearly, the moment generating function will exist if t equals 0. Any other values of t where it has to exist? So let's think about what the moment generating function looks like. So we know it exists when t equals 0. The question is, must it exist elsewhere? So the moment generating function of x of t is the integral from -infinity to infinity of e to the tx times the density. Can you think of any values of t where I know this integral will be fine? Or do we only know that it has to hold at t equals 0? Yes? So if t is negative, then we would have something that's exponentially decreasing. But it's only exponentially decreasing for positive x. So if you take e to the negative x, if you take t equals 1, over here, the function is rapidly decaying. But as you go to the left of 0, it's rapidly increasing. So if my density is all on the negative side, it's going to blow up. Conversely, if you take t equals -1, I'm doing t equals -1 here, sorry. Conversely, if you take t equals 1, it's the other thing. The only value of t where we know it holds is t equals 0. And the problem is e to the tx is exponentially growing in one direction, and it's exponentially decreasing in the other. So what you would hope is that, well, at least, depending on what my density is, hopefully in one direction, it will be fine. If I have a one-sided density, then it should be OK. What we really want to have happen is we want the moment generating function to exist in a small neighborhood, a small interval about 0. And if we have that, then we can do a lot of analysis. So let's take, somebody give me a really bad density to look at. Yes? The Cauchy, right? If you ever need a density to cause trouble, take the Cauchy. Why is the Cauchy the poster boy for bad densities? Yes? It has no mean, it has infinite variance. If we try to take the moment generating function of the Cauchy, we're going to have the integral from -infinity to infinity of e to the tx over 1 plus x squared dx. We have a 1 over pi. And this is going to blow up if t does not equal 0. So it equals infinity if t does not equal 0. So the moment generating function for the Cauchy only exists at t equals 0, and at t equals 0 it's trivial to exist. This is one of the reasons why we do not like the moment generating function. The moment generating function of a lot of random variables does not exist. I'm not going to call it exists because it exists at t equals 0. To me, that's not acceptable. Exists means it must exist in some neighborhood about 0. And the problem is the exponential function is growing rapidly in one direction. This is the advantage of the characteristic function. If we looked at the characteristic function of the Cauchy, this would be the 1 over pi, the integral from -infinity to infinity of e to the I tx over 1 plus x squared dx. And I think we've done this before. E to the I theta is cosine theta plus I sine theta. The absolute value of e to the I theta equals 1. The characteristic function always exists because this extra part over here is of absolute value at most 1. I'm sorry, is of absolute value 1. And in fact, you're typically going to have a lot of oscillation because the real and the imaginary parts oscillate between -1 and 1. And you would expect to have cancellation. The characteristic function always exists. And this is why we study characteristic functions and not moment generating functions later. All right? This is not a class using complex analysis. I'm going to do things in terms of the moment generating function. It's not that much more work to do the characteristic function, but the moment generating function I think is just a little bit easier the first time you see it. You don't have to go through all these I's. All right. I have given it the name moment generating function. I have not justified the name. Right? If you are naming something, you should try to give it a good name. Why do you think we might call it the moment generating function? Yeah, I mean, it's tough to say this without laughing. Right? It generates the moments. Okay? So let me show you how the moment generating function generates the moments. So moment generating function generates moments. And so let's recall the nth moment is the expected value of x to the n. It's the integral from -infinity to infinity of x to the n times the density. And the prime means it's not centered. If I drop the prime, I would be looking at x minus mu to the n. And I'd be looking at the centered moment. All right, so somehow, when we analyze the generating function, the moment generating function, we should be getting the moments to be popping out. So let's look at the moment generating function of x. That's the expected value of e to the tx. Well, it seems to make sense. Let's write down what the integral is. It's the integral from -infinity to infinity of e to the tx times the density. All right. What should we do now? I want to somehow get the moments. What should I do? Well, I don't want to take t to be log x because then t is depending on x. X is a variable of integration. And I can't have t depend on x. We're trying to get things like x to the n times the density. We don't have x to the n. We have e to the tx. So this is giving us a clue as to how to do the algebra. How should we try to do the algebra? So if I take derivatives with respect to t, I would have to know what the moment generating function is. I would have to have a closed form expression for that, which we don't have, unfortunately. I mean, it's not very, but then you'd be taking the log of an integral. How can I get an x to the n? This part looks good, right? I want to have integrals of x to the n. I have an e to the tx. How can I get an x to the n? Yeah, expand it, right? And is that a engineering hat you're wearing today?
No.
You sure? Because an engineering hat allows me to interchange sums and integrals without worrying about convergence. It'd be really convenient if that was an engineering hat. Damn it. Does anybody have an engineering hat? I'd buy one. They're worth having. So they allow you to just switch orders without worrying. So this is the same as the integral from minus infinity to infinity. The sum, n goes from 0 to infinity, of t to the n, x to the n, over n factorial, fx of x, dx. And now I'm not going to worry about justifying the interchange. This is what you would do in an advanced class. How many of you have seen Fubini's theorem from Calc 3, where you have to justify when you can switch the order of integration? And the best result, like Fubini-Tonelli, is if you put in absolute values. If the double integral of the absolute value is finite, then you can switch orders. And so, depending on how things are, you can often justify switching the orders. And so, let's just pretend we can do that. This will become the sum, n goes from 0 to infinity. And then what I'm going to do is I'll have the integral from minus infinity to infinity of x to the n, fx of x dx, and then I'll have a t to the n over n factorial. Because t to the n over n factorial doesn't depend on x, so I can pull it outside the integration. Well, by definition, this is just going to be the nth moment. So we get the sum, n goes from 0 to infinity, the nth moment over n factorial times tn. And this is why we call it the moment generating function. And so if you take a couple of derivatives, you'll see the n will come down and cancel the n factorial. And that's going to be extremely nice. So if x was exponential with parameter lambda, we only calculated the generating function, not the moment generating function, right? Right. We got the generating function of x at s was 1 over 1 minus lambda log s. Right? We did this earlier today. But we know that there's a connection between the generating function and the moment generating function. I could do the calculation all over again and just calculate the moment generating of the exponential, or we could use our change of variables. This was the expected value of s to the x. For the moment generating function at t, this was the generating function at what point? E to the t. And so this should just be 1 over 1 minus lambda t. And again, I could do the calculation the long way. I don't want to. I want to take advantage of the fact that we've got this nice connection. This is equal to, let's expand things out. It's equal to 1 plus mu1 t plus mu2 prime over 2 factorial t squared plus mu3 prime over 3 factorial t cubed plus dot 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 dot. And I'm just writing mu1 prime as mu because that's how we write the mean. And the 0 term is just going to be 1. Okay, so now we have the moment generating function. If I want to calculate what happens at t equals 0, well, I'm getting the expected value basically of 1. All these terms vanish, I get 1, no problem. Now let's say I want to calculate the mean. How do I calculate the mean? If I take one derivative and then set t equal to 0, all of these other terms won't contribute. So if I calculate the first derivative, mx prime of t, I take the derivative, this is 1 minus lambda t inverse. So I'm going to have a negative, and then a negative makes it a positive. I'll get a 1 minus lambda t to the negative 2 times lambda. And when I take a derivative, I'll get mu plus mu2 prime. The 2 over 2 factorial gives me a 1 factorial t plus mu3 prime. 3 with a 3 factorial will give me a 2 factorial t squared plus dot 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 dot. If I now take t equals 0, I'm going to get the mean. So t equals 0, we get mx prime of 0 is equal to lambda, which is the mean. This shows you the power of the moment generating function. If I want to calculate the second moment, I would just take another derivative. And so now, let's take a second derivative. And so now we would get mx double prime of t. So we have a 1 minus lambda to the negative 2. We'll have a negative 2, 1 minus lambda t to the negative 3. The negative comes out, that reinforces. So we get 2, 1 minus lambda t to the negative 3 lambda squared. And that will be equal to mu2 prime plus mu3 prime over, we had 2 factorial over 1 factorial t plus dot 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 dot. So now if we take t equals 0, that gives us 2 lambda squared is mu2 prime. And so now the variance is the expected value of x squared minus the square of the expected value, which is going to be 2 lambda squared minus lambda squared, which is lambda squared. And that's the variance of the exponential. So this is showing you the power. Okay? So if I just keep taking derivatives of this, I can get all these quantities. There is another approach. I don't have to take derivatives. There's a secret back door. Anybody see how I can calculate the mean and the second moment without taking derivatives? Any thoughts? This is a trick that's not emphasized nearly enough in calculus. Can I erase this part over here? All right, so let's go back and let's write the moment generating function. So the moment generating function we saw was 1 over 1 minus lambda t, and this was 1 plus mu t plus mu2 prime over 2 factorial t squared. This should be screaming at you. What is this screaming? Yes, say it loudly. Geometric series, right? We know how to expand this. This is equal to 1 plus lambda t plus lambda squared t squared plus dot dot dot. This is a geometric series. Well, they've got to be equal term by term. Therefore, mu equals lambda, and mu2 prime over 2 factorial equals lambda squared, so it equals 2 lambda squared. We don't even have to take derivatives. We can just expand things out. So they don't really show this trick nearly enough in calculus. It's wonderful. If you can just Taylor expand, you don't have to do all the derivatives. You only have to do enough to see what's going for. So the last question about this, this is a great example. For what value of t is this well defined? So for what value of t will the moment generating function exist? Any thoughts? I'm sorry? Yeah, so we're going to be okay if t is less than 1 over lambda. Now, if we wanted to use this expansion, we would have to be a little bit careful. We might want the absolute value of t to be less than 1 over lambda. So I'm happy to be a little extra safe. If t is a really large negative number, our function is only defined on the positive values. We would have a really big exponential decay. The moment generating function will still exist. But if I want to expand things out like this, if I want this series to be nice, I might want t to be less than 1 over lambda in absolute value. Okay? So this highlights all the different things you can do with the moment generating function. And it's giving you, very similar to the generating function, a series where the coefficients have meaning. And rather than the meaning being the probability of a specific value, it's now giving you the moments. And the idea is similar to a Taylor series. If you know all the Taylor coefficients, you hope you know the function. This is sadly not always the case. There are bad functions like e to the minus 1 over x squared. But most functions hopefully are nice. And the plan will be that somehow we can go from these nice functions and get something meaningful. Okay? So what I want to end today with is a big theorem. The proof is not so bad. And I think some of it we've already done. So theorem. So x is a random variable. And then we have 1. The moment generating function of x at t is 1 plus mu 2 prime over 2 factorial t squared. Okay, well, we've already proved that, so that one's not so bad. 2, alpha and beta are constants. Then, here. And I also want to say in particular that mu k prime is the kth derivative at 0. And we showed this one. Then alpha beta constants, then the moment generating function of alpha x plus beta at t is equal to e to the beta t times the moment generating function of x at alpha t. And then the last one is that I think we want it independent. So x1, x2 are independent. Then the moment generating function of x1 plus x2 of t is the moment generating function of x1 of t, moment generating function of x2 of t. And we have something similar if we have more variables. More generally, the moment generating function of x1 plus xn of t is the moment generating function of x1 of t, moment generating function of xn of t. And then if all the random variables have the same density, this would be maybe the moment generating function of x of t to the n if they have the same density. And so when we start adding independent random variables, this is the case we're going to be in. So there's 3 statements here. 2 of the 3 we've already proved. We already proved the first one as to the expansion of the moment generating function. This is why it has its name. When did we prove this? Yes?
Well, we proved it for generating.
When we proved it for generating functions, right? Mathematicians are lazy. Whenever possible, reduce it to a previously solved problem. So we've already proved this. The only one that's left is 2. So if there's time after class, I will tell a really bad joke about burning houses, reducing things to previous riddles. All right, how do we prove 2? So we want to study the moment generating function of alpha x plus beta at t. How should we start? What should line 1 be of the proof? And what are your thoughts? How would we start this? Yeah, when you prove all of your calculus results, all of your calculus rules of differentiation, you always start with the definition of the derivative. Your function a of x might be f of x times g of x. It might be f of x over g of x. It might be f of g of x. You always start with, it's the limit as h goes to 0 of a of x plus h minus a of x over h. So here, our definition is it's the expected value of e to the t times my random variable, alpha x plus beta. And now you can see the power of the expectation. This is the same as the expected value of e to the alpha tx, e to the beta t. And I'm taking the expectation with respect to x. I'm integrating this times the density. What can you tell me about this number e to the beta t? Yes? It doesn't depend on x. I can just pull this out. It's e to the beta t. And I have the expected value of e to the alpha t x. And I'm deliberately putting this in parentheses to try to remind us of how we should view this. This is almost the moment generating function of x evaluated at t. The only difference is rather than having it at t, I have it at alpha t. And so we get it's e to the beta t moment generating function of x, but now at alpha t. And that finishes the proof. So the moment generating functions inherit a lot of properties from the generating functions. This is a real good start to the proof of the central limit theorem. This is one of the biggest results in math and stats. So many things are normally distributed. The hardest part about all of this is finding a way to do the algebra. Or maybe the hardest part is actually justifying that you can do the algebra the way you want, that you can do the calculations. And there's going to be a lot of complex analysis lurking in the background to justify these things. We already had an interchange of an integral and a sum today. That has to be justified. It's not always the case. But if you can do that, boy, can we advance. Boy, can we do lots of things. Okay? So now that we have that, we actually have fast ways to calculate moments. If you want, as a nice exercise, go back and try to compute the mean and the variance of the Gaussian, the mean and the variance of a binomial random variable. If you can write down what the moment generating function is, and you can either expand it, like I did showing you the Taylor series trick, or by just taking derivatives, you can calculate this. This is a new technique in addition to differentiating identities, in addition to doing the brute force sums or integrations. All right, so this is a good place to stop, and then we will begin our assault, I believe, on the central limit theorem the next time. All right.